White holes are fascinating theoretical objects in astrophysics, predicted by the equations of general relativity. Unlike black holes, which pull matter in, white holes are thought to expel matter and energy. Imagine a black hole in reverse, and you get the basic idea of a white hole. The concept challenges our understanding of the universe and pushes the boundaries of modern physics. Exploring white holes helps us delve deeper into the mysteries of space-time. The foundation of white holes lies in Einstein's field equations, which describe the gravitational effects of mass and energy on space-time. These equations suggest that if black holes exist, their time-reversed counterparts, white holes, could also exist. In this theoretical framework, a white hole appears as a solution to the same equations that describe black holes. However, while black holes have been widely studied and observed, white holes remain hypothetical. One of the defining features of white holes is their event horizon, which is a boundary that nothing can enter. This is the opposite of a black hole's event horizon, where nothing can escape. In a white hole, matter and radiation are ejected, preventing anything from entering. This property makes white holes intriguing, but also raises questions about their stability and formation. Theoretical models of white holes suggest they could be connected to black holes through a wormhole, forming what is known as an Einstein-Rosen bridge. This bridge would theoretically allow travel between different regions of space-time. While this concept is captivating, it remains purely speculative without observational evidence. Nonetheless, it provides an exciting avenue for exploring the nature of the universe. White holes challenge the conventional understanding of entropy and thermodynamics. In black holes, entropy increases as they absorb matter and energy, leading to the eventual evaporation through Hawking radiation. White holes, however, would appear to decrease entropy by expelling matter, contradicting the second law of thermodynamics. This paradox is a significant point of contention and interest among physicists. The notion of white holes also intersects with the study of singularities, which are regions of infinite density and gravitational pull. In black holes, singularities exist at their cores, representing points where our current understanding of physics breaks down. White holes, being time-reversed black holes, would have singularities that expel matter and energy instead of attracting them. Understanding these singularities could provide insights into the fundamental nature of spacetime. While no direct evidence of white holes has been observed, some indirect clues have been proposed. For instance, certain high-energy astrophysical phenomena, such as gamma-ray bursts, have been speculated to involve white holes. However, these interpretations remain highly speculative and require further investigation. The lack of observational evidence is a significant hurdle in confirming the existence of white holes. The theoretical existence of white holes also raises questions about their formation. Black holes are formed from the collapse of massive stars, but there is no known process that would naturally lead to the creation of a white hole. Some theories suggest that white holes could be remnants from the early universe, but this idea remains highly controversial. The formation and stability of white holes are major areas of theoretical research. Exploring white holes also involves understanding the interplay between general relativity and quantum mechanics. These two pillars of modern physics often produce conflicting predictions when applied to extreme conditions, such as those near a black hole or a white hole. The reconciliation of these theories is one of the greatest challenges in physics. White holes provide a unique testing ground for these ideas. Quantum effects, such as quantum tunneling, might play a role in the behavior of white holes. In black holes, quantum tunneling leads to the phenomenon of Hawking radiation, where particles escape from the event horizon. A similar process in white holes could theoretically allow matter to be ejected. These quantum processes are complex and not fully understood, but they offer a potential window into the nature of white holes. Despite the lack of empirical evidence, the study of white holes is driven by their potential implications for cosmology. If white holes exist, they could have a profound impact on our understanding of the universe's structure and evolution. They might be linked to the Big Bang, representing a phase in the early universe where matter and energy were expelled in all directions. This connection could offer new insights into the origin of the universe. Another intriguing aspect of white holes is their potential role in the cosmic cycle. Some theories propose that black holes and white holes could be part of a cyclical process, where matter and energy are continually recycled through different phases of the universe. This idea, while speculative, provides a fascinating perspective on the nature of existence and the universe's long-term behavior. Critics argue that white holes, as currently understood, are too unstable to exist in our universe. Any slight perturbation could cause a white hole to collapse or transform into a black hole. This instability presents a significant challenge to the concept of white holes. However, ongoing research aims to address these issues and explore whether stable white holes could theoretically exist. Recent advancements in theoretical physics have revived interest in white holes. New models and simulations are being developed to explore the conditions under which white holes might form and behave. These studies are crucial for understanding whether white holes can be integrated into our existing framework of the universe. The results of these efforts could either support or refute the existence of white holes. The debate over white holes also touches on the broader question of how we understand and interpret the universe. The existence of white holes would challenge many established concepts and force a re-evaluation of our understanding of space-time. Whether or not white holes are ultimately proven to exist, the pursuit of this question drives innovation and discovery in theoretical physics. Our journey today aims to unravel one of the most intriguing concepts in astrophysics. We're delving into the mysterious world of white holes. This video will guide you through the theories and ideas surrounding these fascinating objects. We'll explore how white holes could potentially reshape our understanding of the cosmos. Understanding white holes starts with grasping their theoretical foundations. By explaining the core principles, we can appreciate the complexities involved. This knowledge forms the bedrock of our exploration. We'll connect these ideas to broader astrophysical phenomena, making the subject more accessible. White holes are not just theoretical constructs. They challenge our perception of reality. This video will highlight their significance in modern physics. We'll examine how they fit within the framework of general relativity. Understanding their role could offer new insights into the nature of the universe. We aim to compare and contrast white holes with black holes. By doing so, we can appreciate their unique characteristics. This comparison will help clarify why white holes are so captivating. Their hypothetical nature adds to their mystique, making them a hot topic for discussion. Exploring the history behind the concept of white holes will provide context. This journey will take us through the evolution of scientific thought. Understanding the origins of these ideas helps us see how far we've come. It also sets the stage for current and future research. We'll dive into the evidence and observations related to white holes. Although direct evidence is lacking, indirect clues exist. This section will present the current state of research. By examining these findings, we can assess the plausibility of white holes in our universe. Thermodynamics and entropy play crucial roles in understanding white holes. This video will explore these complex concepts. We'll discuss how white holes challenge traditional thermodynamic laws. This exploration will reveal the theoretical puzzles that physicists face. Wormholes and time travel are popular topics in science fiction. White holes could theoretically connect to these phenomena. This section will delve into these speculative ideas. By examining these connections, we can appreciate the imaginative scope of white holes. Quantum mechanics is another critical area we'll cover. The intersection of quantum theory and general relativity is crucial for understanding white holes. This video will explain how quantum effects might influence white holes. These insights could bridge gaps in our current theories. Addressing criticisms and counter-arguments is essential for a balanced view. This section will present the skeptical perspectives. We'll explore the main points of contention among physicists. Understanding these criticisms helps us evaluate the validity of white hole theories. Recent research and developments will also be highlighted. We'll look at the latest theoretical advancements and simulations. This section will show how ongoing studies are pushing the boundaries. By staying updated, we can follow the exciting progress in this field. White holes could have profound implications for cosmology. This video will explore their potential impact on our understanding of the universe. We'll discuss how they might influence theories about cosmic evolution. These insights could lead to paradigm shifts in cosmology. Our goal is to provide a comprehensive overview of white holes. By the end of this video, you'll have a deeper understanding of their significance. We aim to spark curiosity and encourage further exploration. The mysteries of white holes await those who seek to unravel them. We'll also touch on the speculative nature of some white hole theories. This section will clarify which ideas are more widely accepted and which are still debated. Understanding this distinction is crucial for appreciating the current state of research. It helps us navigate the landscape of theoretical physics. Ultimately, this video seeks to inspire wonder and curiosity. White holes represent the frontier of our understanding of the cosmos. By exploring these concepts, we join a long tradition of scientific inquiry. The quest to understand white holes is part of humanity's broader journey to comprehend the universe. Black holes are regions in space where gravity is so strong that nothing, not even light, can escape from them. They form when massive stars collapse under their own gravity at the end of their life cycles. The result is a singularity, a point of infinite density, surrounded by an event horizon. The event horizon is the boundary beyond which nothing can return. The concept of black holes dates back to the 18th century, but it was Albert Einstein's theory of general relativity that provided the framework for their understanding. According to general relativity, black holes warp space-time around them. This warping creates a gravitational pull so intense that it bends light and distorts the paths of nearby objects. Black holes come in various sizes, from stellar mass black holes, which are a few times more massive than our Sun, to supermassive black holes, which can be billions of times more massive. Stellar mass black holes form from the remnants of massive stars after a supernova explosion. Supermassive black holes, found at the centers of most galaxies, including our own Milky Way, have more mysterious origins. One of the defining features of black holes is the event horizon. This invisible boundary marks the point of no return. Anything that crosses this threshold is inevitably pulled into the singularity. The event horizon's size is proportional to the black hole's mass. For a stellar mass black hole, the event horizon might be only a few kilometers across, while for a supermassive black hole, it can span millions of kilometers. The existence of black holes was confirmed through indirect observations. Scientists have observed the effects of black holes on nearby stars and gas clouds. For instance, when a star passes too close to a black hole, it can be torn apart in a process called spaghettification. The resulting high-energy emissions are detectable by telescopes, providing evidence of a black hole's presence. Hawking radiation is a theoretical prediction about black holes made by physicist Stephen Hawking. According to this theory, black holes can emit radiation due to quantum effects near the event horizon. This radiation causes the black hole to lose mass, and over incredibly long timescales, can lead to its eventual evaporation. Hawking radiation bridges the gap between quantum mechanics and general relativity. The study of black holes has profound implications for our understanding of physics. They challenge our concepts of space, time, and gravity. By studying black holes, scientists hope to unlock the secrets of the universe's most extreme environments. These insights could lead to breakthroughs in our understanding of the fundamental forces that govern the cosmos. Black holes also play a crucial role in galaxy formation and evolution. The supermassive black holes at the centers of galaxies influence the motion of stars and gas within the galaxy. Their powerful gravitational pull can drive the formation of stars and even regulate the growth of the galaxy itself. Understanding this relationship is key to understanding the universe's large-scale structure. Despite their name, black holes are not empty voids. They are incredibly dense regions where a massive amount of matter is compressed into a tiny space. This extreme density gives them their powerful gravitational pull. The more mass a black hole has, the stronger its gravitational force, affecting everything in its vicinity. The discovery of gravitational waves has opened a new window into the study of black holes. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as when two black holes merge. Detecting these waves allows scientists to observe black hole mergers directly, providing new insights into their properties and behavior. Accretion disks are another important aspect of black holes. When matter falls towards a black hole, it often forms a rotating disk around it. The friction and gravitational forces within the accretion disk heat the matter, causing it to emit X-rays and other radiation. Observing these emissions helps scientists study the properties of black holes and their interactions with surrounding matter. Black holes can also produce powerful jets of particles. These jets are ejected from the regions near the event horizon at nearly the speed of light. They can extend for thousands of light years, affecting the interstellar medium and even influencing the evolution of entire galaxies. The mechanisms behind these jets are still not fully understood, making them a subject of ongoing research. The information paradox is a major puzzle in black hole physics. It arises from the question of what happens to information about the matter that falls into a black hole. According to quantum mechanics, information cannot be destroyed, but it seems to be lost when a black hole evaporates. Resolving this paradox could lead to a deeper understanding of quantum gravity. Black holes are often depicted in popular culture, from movies to books, capturing the public's imagination. While these portrayals are not always scientifically accurate, they reflect the fascination and mystery surrounding these cosmic objects. Black holes remain a compelling subject for both scientific inquiry and public interest. As we continue to study black holes, we uncover more about the fundamental nature of the universe. Each discovery brings new questions and challenges our understanding of physics. Black holes are not just cosmic curiosities. They are key to unlocking the deepest secrets of our universe. The study of white holes holds significant importance in astrophysics. It challenges our understanding of the universe and pushes the boundaries of current scientific knowledge. White holes represent one of the most intriguing theoretical concepts, offering a counterpoint to the well-established black holes. White holes force us to revisit the fundamental laws of physics. Their hypothetical existence questions the principles of thermodynamics and general relativity. Exploring these questions can lead to new insights and potentially groundbreaking discoveries in theoretical physics. Investigating white holes can provide a deeper understanding of space-time. These objects are crucial in studying the nature of singularities and event horizons. By exploring these extremes, we can gain a better grasp of the fabric of the universe itself. The concept of white holes ties into the broader study of cosmic evolution. They could play a role in the birth and death cycles of celestial bodies. Understanding this process is essential for building a complete picture of the universe's history and future. White holes also have implications for quantum mechanics. They offer a unique context for studying the intersection of quantum theory and general relativity. This intersection is key to developing a unified theory of quantum gravity, one of the greatest challenges in modern physics. White holes could be connected to the study of wormholes and time travel. These concepts, while speculative, open up fascinating possibilities for the structure of space-time. Exploring white holes might help us understand whether such exotic structures can exist. Astrophysics benefits from interdisciplinary studies, and white holes are a perfect example. They require knowledge from various fields, including general relativity, quantum mechanics, and thermodynamics. This interdisciplinary approach fosters collaboration and innovation. The search for white holes drives technological advancements in observational tools. Improving these tools enhances our ability to detect and study other cosmic phenomena. These advancements have wide-ranging applications beyond just white hole research. White holes contribute to our understanding of black hole dynamics. By studying their theoretical counterparts, we can learn more about black hole formation, behavior, and evaporation. This comparative study enriches our overall knowledge of these enigmatic objects. Public interest in white holes can inspire future generations of scientists. These captivating topics encourage curiosity and a passion for discovery. By engaging with the public, scientists can promote education and foster a deeper appreciation for astrophysics. Exploring white holes can lead to a better understanding of the universe's asymmetries. They challenge the notion of a purely symmetrical cosmos. Investigating these asymmetries can reveal hidden aspects of the universe's structure and evolution. White holes might offer explanations for unexplained cosmic phenomena. Certain high-energy events could be linked to these theoretical objects. Understanding white holes could provide answers to some of the most puzzling questions in astrophysics. Theoretical work on white holes contributes to the broader field of cosmology. It helps refine our models of the universe and its origins. This research can lead to new theories and paradigms, shifting our perspective on the cosmos. Ultimately, the importance of studying white holes lies in their potential to revolutionize our understanding of the universe. They represent the unknown, pushing the frontiers of science. The pursuit of knowledge about white holes embodies the essence of scientific inquiry and discovery. The formation of black holes begins with massive stars. These stars, much larger than our Sun, undergo a life cycle that culminates in a dramatic end. Throughout their lives, these stars fuse hydrogen into helium in their cores, producing immense amounts of energy. As a massive star ages, it exhausts its hydrogen fuel. The core then contracts and heats up, igniting fusion of heavier elements like helium, carbon, and oxygen. This process continues, forming progressively heavier elements until iron accumulates in the core. Iron fusion does not produce energy. Instead, it consumes energy, leading to a critical point. When the core's pressure can no longer counteract the gravitational forces, it collapses in a fraction of a second. This collapse is so intense that it triggers a supernova explosion, the outer layers of the star blasted into space. The core's collapse during a supernova is a key moment. If the core's remaining mass is above a certain threshold, known as the Tolman-Oppenheimer-Volkoff limit, it cannot support itself against gravity. This threshold is approximately 3 times the mass of our Sun. When the core's mass exceeds this limit, it continues to collapse into an extremely dense point, forming a singularity. This singularity is the heart of a black hole, where densities and gravitational forces become infinite. The region surrounding this singularity is the event horizon, beyond which nothing can escape. Not all supernovae result in black holes. If the core's mass is below the critical limit, it forms a neutron star instead. Neutron stars are incredibly dense, but not dense enough to create a singularity. The difference in outcomes is determined by the core's final mass. Black holes can also form through other processes, such as stellar collisions. When 2 massive stars collide, their combined mass can exceed the limit needed to form a black hole. This rare event results in a single, larger black hole, highlighting the diverse pathways to black hole formation. In addition to stellar mass black holes, there are supermassive black holes found at the centers of galaxies. These giants, millions to billions of times the mass of the Sun, likely formed through different processes. One theory suggests they grew from smaller black holes, accumulating mass over billions of years. Another possibility for supermassive black hole formation is the direct collapse of massive gas clouds in the early universe. These clouds, free of the constraints of fusion, could collapse directly into black holes without the intermediate step of star formation. This process could explain the presence of supermassive black holes in young galaxies. Black holes can also grow by accreting matter from their surroundings. When a black hole is part of a binary system, it can pull matter from its companion star. This matter forms an accretion disk around the black hole, heating up and emitting X-rays before crossing the event horizon. The discovery of gravitational waves has provided new insights into black hole formation. These waves are ripples in space-time caused by the acceleration of massive objects, such as merging black holes. The detection of these waves confirms that black holes can form through mergers, adding another pathway to their formation. Primordial black holes are another theoretical possibility. These black holes could have formed in the early universe, shortly after the Big Bang. Fluctuations in the density of matter could have created regions dense enough to collapse into black holes, providing a potential explanation for certain cosmic phenomena. The formation of intermediate mass black holes remains a mystery. These black holes, with masses between stellar mass and supermassive black holes, are harder to detect. Understanding their formation requires further observation and theoretical modeling. The life cycle of a black hole continues after its formation. Over time, black holes can merge, grow, and influence their surroundings. Their formation processes are critical for understanding the dynamics of galaxies and the evolution of the universe. Research into black hole formation is ongoing. Advanced simulations and observations continue to refine our understanding of these enigmatic objects. Each discovery brings us closer to unraveling the complexities of black hole formation and their role in the cosmos. The hypothetical formation of white holes is a subject of intense speculation in theoretical physics. Unlike black holes, white holes are not formed from collapsing stars. Instead, they are proposed as solutions to the equations of general relativity, representing a reverse process. One idea is that white holes could have formed in the early universe. During the Big Bang, conditions were extreme, with incredibly high temperatures and densities. Some physicists suggest that white holes might have emerged from these primordial conditions. Another hypothesis involves the evaporation of black holes. As black holes emit Hawking radiation, they lose mass over time. Some theories propose that when a black hole evaporates completely, it could transform into a white hole, expelling all remaining energy and information. Quantum gravity theories offer alternative formation mechanisms for white holes. In loop quantum gravity, black holes might avoid a singularity and bounce back as white holes. This process, called a quantum bounce, suggests that white holes are the reborn state of evaporated black holes. White holes might also be linked to the concept of wormholes. A wormhole connects two different regions of spacetime, potentially linking a black hole at one end to a white hole at the other. If wormholes exist, they could facilitate the creation of white holes in a connected universe. Cosmic inflation, a rapid expansion of the universe after the Big Bang, could also play a role. Some models of inflation suggest that fluctuations in the early universe might create conditions suitable for white hole formation. These white holes could then be remnants of that inflationary period. Hypothetical scenarios also consider white holes as parts of black hole interiors. In these models, the inside of a black hole might contain a region that behaves like a white hole, where matter and energy are expelled rather than consumed. This idea remains speculative and controversial. White holes could also be theorized as mirror images of black holes in an anti-universe. In this symmetrical universe, time flows backward relative to ours, making white holes the counterparts of black holes. This concept challenges our understanding of time and causality. The concept of white holes challenges the second law of thermodynamics, which states that entropy always increases. If white holes decrease entropy by expelling matter, they would violate this law. This paradox is a significant hurdle in the theoretical acceptance of white holes. Some physicists propose that white holes might appear spontaneously through quantum fluctuations. In the quantum realm, particles and antiparticles constantly pop in and out of existence. Similarly, white holes could briefly appear and disappear in spacetime, though this idea remains highly speculative. Mathematical models predicting white holes rely on precise initial conditions. These conditions, necessary for white hole formation, might be so specific that they are improbable in our universe. This rarity makes white holes an unlikely but intriguing possibility. The stability of white holes is another major concern. Any small disturbance could cause a white hole to collapse or transform. This instability suggests that even if white holes could form, they might not last long enough to be observed. White holes might also be involved in the recycling of the universe. In some cyclic cosmological models, the universe undergoes infinite cycles of birth and death. White holes could be the outflow points of matter and energy from previous cycles, contributing to the rebirth of the universe. Despite the lack of observational evidence, the study of white holes helps physicists test the limits of general relativity and quantum mechanics. These hypothetical objects push the boundaries of our understanding and inspire new theories about the universe's fundamental nature. Research into white holes continues to be a fascinating and speculative area of theoretical physics. By exploring these hypothetical formations, scientists aim to uncover deeper truths about the nature of spacetime, the origins of the universe, and the ultimate fate of cosmic objects. The event horizon of a black hole is a boundary beyond which nothing can escape. It marks the point where the gravitational pull becomes so strong that not even light can break free. In contrast, the event horizon of a white hole is a boundary that nothing can enter. Matter and energy can only move outwards from this horizon, making it a region of perpetual expulsion. For black holes, the event horizon is associated with the point of no return. Anything that crosses it is inexorably drawn towards the singularity. This inward pull defines the black hole's ability to trap everything, including light, leading to its characteristic darkness. White holes, however, have an event horizon that acts as a barrier to entry. Instead of pulling objects in, it pushes everything out. This outward force creates a repulsive boundary, making white holes essentially the mirror image of black holes in terms of their event horizons. The surface area of a black hole's event horizon increases as it absorbs more matter and energy. This growth is a fundamental aspect of black hole thermodynamics, where the event horizon's area is directly related to the black hole's entropy. For white holes, the theoretical increase in surface area would be associated with the expulsion of matter and energy, a concept that challenges our current understanding of entropy. In black holes, time appears to slow down near the event horizon due to intense gravitational effects. This phenomenon, known as time dilation, means that an observer far from the black hole would see time near the event horizon progressing much more slowly. For white holes, time would theoretically behave in an opposite manner, potentially speeding up as one moves away from the event horizon. The event horizon of a black hole can emit Hawking radiation, a quantum effect that causes black holes to lose mass over time. It's unclear whether white holes would emit a similar form of radiation, but if they did, it would likely involve a very different mechanism, given their repulsive nature. Accretion disks form around black holes as matter spirals inwards before crossing the event horizon. These disks are sources of intense radiation and high-energy particles. White holes, in contrast, would not have accretion disks. Instead, they would eject matter, possibly forming outflowing streams or jets, rather than inward spiraling disks. The shape and size of a black hole's event horizon depend on its mass and rotation. Non-rotating black holes have spherical event horizons, while rotating ones are oblate spheroids due to their angular momentum. White holes, if they exist, would exhibit similar dependencies, with their event horizons shaped by their mass and rotational dynamics. The information paradox is a significant issue for black holes, concerning the fate of information that falls beyond the event horizon. In white holes, the paradox might be inverted, focusing on how information is expelled and whether it is preserved or lost during the process. Black holes can merge, forming larger black holes with combined event horizons. The resulting gravitational waves from such mergers have been detected and provide insights into black hole properties. For white holes, hypothetical mergers would involve the interaction of repulsive forces, a scenario that is not well understood and lacks observational evidence. Observing a black hole involves detecting the effects on nearby matter, such as gravitational lensing and X-ray emissions from accretion disks. White holes, on the other hand, would be observed through the expulsion of matter and energy, creating a very different set of observational signatures. The event horizon of a black hole is a well-defined boundary with significant physical and observational implications. White holes, with their theoretical event horizons, pose more abstract and speculative challenges, highlighting the differences in our understanding and the limitations of current models. In both black holes and white holes, the event horizon represents a boundary of extreme gravitational effects. For black holes, it signifies a region of no escape, while for white holes, it marks a boundary that cannot be crossed from the outside. This fundamental difference defines their respective roles in the universe. The concept of an event horizon is central to both black holes and white holes, emphasizing their nature as solutions to the equations of general relativity. While black holes are well supported by observational evidence, white holes remain hypothetical, their event horizons purely theoretical constructs. Comparing the event horizons of black holes and white holes highlights the symmetry and differences between these two fascinating objects. This comparison deepens our understanding of the extreme conditions predicted by general relativity and challenges us to expand our theoretical and observational horizons. The singularity is the heart of a black hole, a point where gravity crushes matter to infinite density. At this point, the laws of physics as we know them break down, and our understanding of space-time becomes incomplete. This infinite density creates a gravitational pull so strong that it warps the fabric of space-time. In black holes, the singularity is hidden within the event horizon. This makes it inaccessible to outside observers, shielding it from direct observation. The event horizon acts as a boundary that prevents any information about the singularity from escaping. White holes, if they exist, would also contain singularities. However, instead of pulling matter in, a white hole's singularity would expel matter and energy. This difference in behavior highlights the contrasting nature of these two hypothetical objects. The singularity of a white hole is a point of infinite density, just like in black holes. However, the repulsive nature of white holes suggests that their singularities would push matter and energy outward. This repulsion creates a fundamentally different interaction with space-time. Theoretical models of singularities often rely on solutions to Einstein's equations. In both black holes and white holes, these solutions predict regions of infinite curvature. This curvature represents the intense gravitational effects near the singularity. One of the key challenges in understanding singularities is their infinite nature. Infinite density and curvature are difficult to reconcile with the finite values we observe in the universe. This discrepancy suggests that our current theories may be incomplete. Quantum mechanics offers potential insights into the nature of singularities. Some theories suggest that quantum effects could smooth out the infinities, preventing true singularities from forming. This quantum perspective aims to unify general relativity with the principles of quantum physics. In loop quantum gravity, singularities might be avoided through a process called a quantum bounce. This theory proposes that instead of forming a singularity, collapsing matter could rebound, creating a white hole. This bounce challenges the traditional view of singularity formation. The information paradox is deeply tied to the nature of singularities. In black holes, information about infalling matter seems to be lost at the singularity. Resolving this paradox is crucial for a complete understanding of black holes and their quantum properties. Theoretical physicists also explore the possibility of naked singularities. These singularities would be visible without an event horizon, exposing their infinite nature. The existence of naked singularities would have profound implications for our understanding of cosmic censorship and the structure of space-time. Singularities in rotating black holes, or Kerr black holes, add another layer of complexity. These singularities form a ring shape rather than a point, creating unique gravitational effects. The rotation influences the geometry of the singularity and the surrounding spacetime. White holes with rotating singularities would theoretically have similar complexities. The expulsion of matter and energy from a rotating singularity could create distinctive patterns in spacetime. These hypothetical scenarios push the boundaries of our understanding. The study of singularities also touches on the origin of the universe. The Big Bang theory suggests that the universe began from a singularity, a point of infinite density. This cosmic singularity represents the starting point for the expansion of the universe. Singularities challenge our understanding of time. Near a singularity, time can behave in unexpected ways, potentially reversing or becoming meaningless. This challenges our everyday experience of time and causality, pushing the limits of theoretical physics. Ultimately, the nature of singularities remains one of the greatest mysteries in science. They represent the frontier of our understanding, where classical physics meets quantum mechanics. Studying singularities in both black holes and white holes could unlock deeper truths about the universe and the fundamental nature of reality. Black holes and white holes exhibit starkly different observable behaviors. Black holes pull matter and energy into them, making them regions of no escape. They are characterized by their intense gravitational pull and the fact that nothing, not even light, can escape once it crosses the event horizon. White holes, by contrast, are theorized to expel matter and energy. Instead of drawing objects in, they push everything outwards. This repulsive force creates an observable difference in how matter interacts with the surrounding space. Accretion disks around black holes are prominent sources of X-rays and other high-energy emissions. Matter spiraling into a black hole heats up and emits radiation. In white holes, we would expect the opposite. Ejected matter and energy could create distinctive emission patterns as they move away from the singularity. Black holes can create powerful jets of particles along their rotational axes. These jets are formed by the intense magnetic fields in the accretion disks. For white holes, any jets would likely be composed of expelled matter, creating outward flowing streams rather than inward swirling disks. Gravitational lensing is a phenomenon observed around black holes. The immense gravitational field bends the light from background objects, creating multiple images or distorted shapes. White holes, with their repulsive nature, would theoretically produce different lensing effects, possibly pushing light away and distorting it in unique ways. The presence of an event horizon is a critical observational feature of black holes. This boundary marks the point of no return. In white holes, the event horizon would be a boundary that cannot be entered, only exited, creating a fundamentally different observational signature. Time dilation occurs near black holes, where time appears to slow down near the event horizon. For white holes, time dilation would manifest differently. As objects move away from a white hole, time might appear to speed up, presenting a unique challenge for observation and measurement. Black holes often reside in binary systems, pulling matter from a companion star. This process creates detectable X-ray binaries. White holes in similar systems would theoretically repel matter, creating outward flows that could be observed as distinctive high-energy emissions. The merger of black holes produces gravitational waves, detectable ripples in space-time. These waves have a characteristic pattern based on the masses and spins of the merging black holes. A white hole merger, if it were possible, would create a different wave pattern, potentially detectable with advanced gravitational wave observatories. The stability of black holes contrasts with the predicted instability of white holes. Black holes can persist for billions of years, while white holes are thought to be highly unstable, quickly dissipating or transforming into black holes if perturbed. The observational data from black hole environments, such as the Event Horizon Telescope's images, show the shadow of a black hole. For white holes, we would expect to see an outward glow from the expelled matter and energy, a stark contrast to the darkness of a black hole's shadow. In galactic centers, supermassive black holes influence the motion of stars and gas clouds. These gravitational effects are observable through the orbital paths of nearby objects. A supermassive white hole would theoretically repel nearby stars and gas, creating a different dynamic observable through telescopes. Hawking radiation causes black holes to lose mass over time, a quantum effect predicted by Stephen Hawking. If white holes emit a similar radiation, it would result in an observable decrease in mass and a potential increase in expelled particles, providing a different form of energy emission. Black holes are associated with phenomena like quasars, an active galactic nuclei, where their immense gravitational pull powers luminous emissions. White holes, if they exist, could create similar but outwardly driven high-energy phenomena, leading to different observational signatures in the universe. The study of black holes has provided a wealth of observational evidence, from X-ray emissions to gravitational waves. White holes remain hypothetical, with no direct observational evidence yet. However, their theoretical behaviors offer a rich field for future exploration, potentially revealing new and exotic cosmic phenomena. The concept of white holes originated from the theoretical framework of general relativity. Albert Einstein's equations predicted various solutions, one of which led to the idea of regions in spacetime that behave oppositely to black holes. This early theoretical groundwork laid the foundation for the concept of white holes. The idea gained further traction through the work of physicist Igor Novikov. In the 1960s, Novikov explored the theoretical properties of white holes and their implications for cosmology. His contributions helped establish white holes as a legitimate area of study within theoretical physics. White holes are closely linked to the Schwarzschild solution of Einstein's equations. This solution describes a spherically symmetric, non-rotating mass in spacetime, which can be interpreted to include both black holes and their time-reversed counterparts, white holes. This mathematical connection is crucial to understanding the origin of the concept. Theoretical explorations of wormholes also contributed to the development of the white hole concept. Wormholes, or Einstein-Rosen bridges, are hypothetical tunnels connecting different regions of spacetime. These bridges suggest a connection between black holes and white holes, with a black hole at one end and a white hole at the other. White holes were further popularized by discussions in the context of the Big Bang theory. Some physicists proposed that the universe's creation could be akin to a white hole, expelling matter and energy into existence. This idea linked white holes to cosmological models and the origin of the universe itself. In the 1970s, Stephen Hawking's work on black hole thermodynamics indirectly influenced thoughts on white holes. While Hawking focused on black holes emitting radiation, the symmetry in theoretical physics encouraged consideration of how similar principles might apply to white holes. The Penrose diagram, developed by Roger Penrose, provided a visual representation of spacetime, including black holes and white holes. This diagram helped physicists conceptualize the relationship between these objects and their roles within the broader framework of general relativity. Discussions of cosmic censorship also touched upon the idea of white holes. The cosmic censorship hypothesis, proposed by Penrose, suggests that singularities are always hidden within event horizons. This hypothesis raises questions about whether white holes, with their exposed singularities, could exist without violating this principle. White holes also found a place in science fiction, capturing the public's imagination. Stories and films featuring white holes helped popularize the concept, even if the scientific basis remained speculative. This cultural impact reflects the intriguing nature of white holes as theoretical objects. The development of quantum gravity theories in the late 20th and early 21st centuries brought new perspectives on white holes. These theories aim to reconcile general relativity with quantum mechanics, potentially providing a framework in which white holes could be better understood. Physicists like Carlo Rovelli and Lee Smolin have explored the possibility of black holes transitioning into white holes through quantum processes. This idea, known as a quantum bounce, suggests that a black hole could eventually expel all its matter and energy as a white hole, challenging traditional views of singularities. White holes remain a topic of debate and speculation within the scientific community. While they are mathematically plausible solutions to Einstein's equations, their physical existence is unconfirmed. This ongoing debate highlights the dynamic nature of theoretical physics and the quest to understand the universe's deepest mysteries. The concept of white holes continues to evolve as new theoretical models and simulations are developed. Advances in computational physics allow for more detailed exploration of how white holes might behave and interact with their surroundings. These efforts keep the study of white holes at the forefront of theoretical research. White holes also raise philosophical questions about the nature of time and causality. Their existence implies a reversal of time's arrow, challenging our intuitive understanding of temporal progression. This philosophical dimension adds another layer of intrigue to the study of white holes. As our understanding of the universe grows, the concept of white holes remains an important area of theoretical exploration. Whether or not they are ever observed, white holes push the boundaries of our knowledge and inspire continued inquiry into the fundamental nature of reality. The concept of white holes has been explored in several key scientific papers and theories. One of the earliest and most influential works was by Carl Schwarzschild in 1916. His solutions to Einstein's field equations laid the groundwork for understanding both black holes and white holes. Igor Novikov made significant contributions to the theory of white holes in the 1960s. His work on the possible existence and properties of white holes helped establish them as a legitimate area of theoretical research. Novikov's ideas were pivotal in bringing white holes into mainstream scientific discourse. Roger Penrose's work on singularities and spacetime also influenced the study of white holes. His development of the Penrose diagram provided a visual framework for understanding the relationship between black holes and white holes. This tool has been crucial in visualizing the complex nature of these objects. Stephen Hawking's theories on black hole radiation, although primarily focused on black holes, also had implications for white holes. Hawking's discovery of radiation emitted by black holes led to questions about whether similar processes could occur in white holes. This intersection of ideas has been a point of interest for physicists. The Reissner-Nordström solution extended the Schwarzschild solution to include electric charge. This solution showed that charged black holes could theoretically have corresponding white holes. This extension of the theory added another layer of complexity to the study of these hypothetical objects. In the context of wormholes, the work of Albert Einstein and Nathan Rosen in the 1930s proposed the concept of Einstein-Rosen bridges. These bridges suggested a connection between black holes and white holes, offering a theoretical framework for understanding how these objects might be linked through spacetime. The cosmic censorship hypothesis, proposed by Roger Penrose, has implications for the existence of white holes. This hypothesis posits that singularities are always hidden within event horizons. The idea challenges the possibility of visible white holes, as their singularities would be exposed. Carlo Rovelli and Francesca Vidotto's work on loop quantum gravity offers another perspective on white holes. Their research suggests that black holes could transition into white holes through a process known as a quantum bounce. This theory attempts to reconcile general relativity with quantum mechanics. Lee Smolin's contributions to quantum gravity theories also touch on the nature of white holes. His work explores the fundamental structure of spacetime and the potential for white holes to emerge from quantum gravitational processes. Smolin's ideas continue to influence contemporary discussions on the subject. Theoretical models of white holes often draw from various aspects of general relativity and quantum mechanics. Papers by physicists like Abhay Ashtekar and Martin Bojewald have explored how these models can be constructed and what they imply for our understanding of the universe. John Wheeler's concept of geons, or gravitational electromagnetic entities, also plays a role in white hole theories. Wheeler's ideas about the nature of spacetime and its interaction with matter and energy provide a broader context for understanding white holes and their potential existence. Recent advancements in computational physics have allowed for more detailed simulations of white holes. These simulations, based on the foundational theories of general relativity and quantum mechanics, help physicists explore the behavior and properties of white holes in a virtual environment. The information paradox, extensively discussed in papers by Leonard Susskind and Gerard 't Hooft, raises important questions about the nature of information in black holes and white holes. This paradox is central to understanding how information is preserved or lost in these extreme environments. The ADS-CFT correspondence proposed by Juan Maldacena has implications for white hole theories. This duality between a gravitational theory in anti-de Sitter space and a conformal field theory on its boundary offers insights into how white holes might be understood within a broader theoretical framework. Overall, the study of white holes is built on a rich foundation of scientific papers and theories. These works continue to drive research and inspire new questions about the nature of spacetime, singularities, and the fundamental laws that govern our universe. Karl Schwarzschild was one of the first scientists to lay the theoretical groundwork for black holes and white holes. His solutions to Einstein's equations are fundamental to our understanding of these objects. Albert Einstein himself, through his theory of general relativity, provided the framework that predicts the existence of white holes. His equations have guided countless physicists in exploring these fascinating concepts. Igor Novikov played a pivotal role in the 1960s by exploring the properties and implications of white holes. His work helped bring white holes into serious scientific consideration and debate. Stephen Hawking's research on black hole radiation opened new avenues for theoretical physics. Although his focus was on black holes, his work has implications for the study of white holes, particularly in the context of thermodynamics and quantum mechanics. Roger Penrose's contributions to our understanding of singularities and spacetime are crucial. His development of the Penrose diagram has been instrumental in visualizing the relationship between black holes and white holes. John Wheeler, with his concept of geons and his extensive work on the nature of spacetime, has provided insights that are relevant to the study of white holes. His innovative ideas continue to influence theoretical physics. Carlo Rovelli and Francesca Vidotto have advanced the study of white holes within the framework of loop quantum gravity. Their research suggests that black holes could transition into white holes, offering a quantum perspective on these objects. Lee Smolin's work in quantum gravity also touches on the potential existence of white holes. His theories explore the fundamental structure of spacetime and how white holes might fit into this picture. Leonard Susskind and Gerard 't Hooft have extensively discussed the information paradox, which is relevant to both black holes and white holes. Their work raises important questions about how information is preserved in these extreme environments. Juan Maldacena's proposal of the ADS-CFT correspondence offers a new way to understand gravitational phenomena, including white holes, through the lens of dualities between different theoretical frameworks. Abhay Ashtekar and Martin Bojewald have contributed to the theoretical models that explore white holes. Their work in loop quantum gravity and cosmology provides a deeper understanding of these hypothetical objects. Robert Wald's research on general relativity and its implications for black holes and white holes has been influential. His work helps us understand the complex behaviors predicted by Einstein's equations. Jacob Bekenstein's work on black hole entropy and the thermodynamics of black holes has indirect implications for white holes. His theories help us think about how entropy might behave in these hypothetical scenarios. Gerard 't Hooft's contributions to particle physics and quantum gravity intersect with the study of white holes. His work continues to inspire new ways of thinking about the fundamental nature of the universe. S.W. Hawking and G.F.R. Ellis, through their collaborative work on the large-scale structure of space-time, have laid the groundwork for much of what we understand about singularities and cosmic phenomena, including the theoretical underpinnings of white holes. The concept of white holes has evolved significantly since its inception. Initially, it was a purely theoretical construct derived from the mathematics of general relativity. Early on, physicists viewed white holes as intriguing, but largely speculative. In the 1960s, Igor Novikov's work brought white holes into more serious scientific discussions. He explored their properties and potential implications, establishing them as a legitimate topic for theoretical investigation. As black hole research progressed, so did the interest in their theoretical counterparts. The discovery of black holes lent credibility to the mathematical solutions that also predicted white holes. This parallel development kept the concept of white holes in scientific discourse. The 1970s saw significant advancements with Stephen Hawking's theories on black hole radiation. While focused on black holes, Hawking's work raised questions about similar processes in white holes, particularly regarding thermodynamics and information theory. During this period, Roger Penrose's contributions to our understanding of singularities and spacetime were pivotal. His Penrose diagrams provided a framework to visualize white holes, aiding in their conceptual development. The exploration of wormholes in the late 20th century also influenced the evolution of white hole theories. Wormholes suggested a connection between black holes and white holes, making the latter more plausible within the broader context of spacetime geometry. Quantum gravity theories in the 1980s and 1990s brought new perspectives. Researchers like Carlo Rovelli and Lee Smolin proposed that white holes could emerge from quantum gravitational processes, particularly in loop quantum gravity. The information paradox, extensively discussed by Leonard Susskind and others, kept white holes relevant. This paradox, which challenges our understanding of information conservation in black holes, indirectly supports ongoing investigations into white holes. Theoretical models continued to evolve with advances in computational physics. Simulations provided new ways to explore how white holes might behave, helping to refine and challenge existing theories. The concept of a quantum bounce, proposed in the early 2000s, suggested that black holes could transition into white holes. This idea added a new layer to the understanding of these objects, integrating quantum mechanics with general relativity. Recent discussions about the holographic principle and the ADS-CFT correspondence have also influenced white hole theories. These ideas propose that the universe can be described by a lower dimensional boundary, offering new insights into gravitational phenomena. Experimental advancements, such as the detection of gravitational waves, indirectly impact white hole research. Understanding black hole mergers and their resulting waves helps refine theories about white hole behavior. Contemporary research continues to explore white holes as potential explanations for various cosmic phenomena. Some physicists propose that certain high-energy events in the universe could be linked to white holes, though this remains speculative. The evolution of the white hole concept reflects broader trends in theoretical physics. As our understanding of the universe deepens, so does the complexity and nuance of white hole theories. Today, white holes remain a fascinating and speculative area of study. While still theoretical, their continued exploration pushes the boundaries of our knowledge and challenges our understanding of the cosmos. The current standing of white holes in the scientific community is one of cautious interest and skepticism. While they are mathematically possible, there is no direct observational evidence to support their existence. This lack of empirical data keeps white holes in the realm of theoretical physics. Most physicists agree that white holes are intriguing but speculative constructs. They are seen as a natural extension of the equations of general relativity, but their physical reality is still in question. This distinction between mathematical possibility and physical reality is a key aspect of their current status. White holes are often discussed in the context of black holes and the broader study of singularities. Their hypothetical nature contrasts with the well-documented evidence of black holes, making them less central to mainstream astrophysics. However, they remain a topic of interest for those studying the extremes of gravitational theory. Theoretical physicists continue to explore white holes as part of their work on quantum gravity. These studies aim to understand how general relativity and quantum mechanics can be unified. White holes, with their challenging properties, provide a unique testing ground for these theories. Recent advances in observational astronomy have not yet detected any signs of white holes. Instruments like the Event Horizon Telescope focus on black holes, but the search for white holes requires different strategies. This ongoing search keeps the question of their existence open. The information paradox, a significant issue in black hole physics, indirectly supports the study of white holes. The paradox involves the fate of information that falls into a black hole, and some solutions to this problem involve scenarios where black holes could transition into white holes. White holes are sometimes considered in cosmological models. Some theories propose that white holes could have been more common in the early universe, potentially influencing cosmic evolution. These ideas are speculative but highlight the ongoing interest in understanding their potential role in the cosmos. Quantum bounce theories, particularly those from loop quantum gravity, suggest that black holes might transition into white holes. These ideas challenge traditional views and propose a cyclical nature of black holes and white holes. This perspective keeps white holes relevant in discussions about the nature of the universe. Educational resources and scientific literature often mention white holes alongside black holes to illustrate the symmetry and completeness of general relativity solutions. This pedagogical use helps students and researchers understand the full scope of Einstein's equations. While white holes are not a focus of major observational programs, they remain a topic of interest at theoretical physics conferences and in academic journals. Discussions about their properties and implications continue to stimulate debate and research. Collaborations between physicists working on different aspects of gravitational theory sometimes include white holes as a point of discussion. These interdisciplinary efforts highlight the broad interest in understanding all possible solutions to Einstein's equations. Some speculative theories suggest that white holes could be linked to dark matter or dark energy. These ideas are far from confirmed, but show the creative ways physicists are trying to explain the mysteries of the universe using theoretical constructs like white holes. Public interest in white holes is often driven by their portrayal in science fiction and popular science media. This interest helps maintain a level of curiosity and funding for theoretical research, even if the primary focus remains on more empirically supported phenomena. The future of white hole research depends largely on advancements in theoretical physics and observational technology. If new methods or instruments could provide indirect evidence of white holes, their standing in the scientific community could change dramatically. For now, white holes occupy a curious position in science, representing both the elegance of theoretical physics and the challenges of empirical validation. Their study continues to push the boundaries of our understanding, reminding us of the vast unknowns that still await exploration in the universe. The lack of direct observations of white holes is a significant challenge in their study. Unlike black holes, which can be detected through their interactions with surrounding matter, white holes remain elusive. Their hypothetical nature makes them difficult to identify using current technology. One reason for this difficulty is that white holes would expel matter and energy, making them appear very different from black holes. Instead of drawing in matter, they would push it away. This fundamental difference means that the methods used to observe black holes may not apply to white holes. Telescopes and other instruments designed to detect black holes rely on the X-rays and other radiation emitted by accreting matter. White holes, however, would not have accretion disks. They might instead produce unique emissions that we have yet to identify or recognize as evidence of white holes. Gravitational wave detectors like LIGO have successfully observed black hole mergers, but detecting white holes would likely require different signals. If white holes exist, their interactions with spacetime could produce distinctive gravitational waves, but these signatures are not yet well understood or predicted. Theoretical models suggest that white holes, if they form, are highly unstable. This instability means they might not last long enough to be observed. They could quickly dissipate or transform into black holes, making direct detection even more challenging. Astrophysicists rely on indirect evidence to study many cosmic phenomena. For white holes, even indirect evidence is scarce. The expected expulsion of matter and energy could theoretically produce detectable phenomena, but no such observations have been conclusively linked to white holes. Cosmological models sometimes include white holes to explain certain aspects of the early universe. However, these models remain speculative, and there is no observational data to confirm the presence of white holes in the cosmos. This lack of data leaves their existence purely theoretical. The concept of white holes challenges our current observational techniques. Innovations in telescope technology and data analysis might one day provide the tools needed to detect them. Until then, white holes remain a fascinating but unobserved possibility. Some researchers propose that high-energy cosmic events, such as gamma-ray bursts, could be linked to white holes. However, these events are usually attributed to other well-understood phenomena, such as supernovae or neutron star mergers. Connecting them to white holes requires more evidence. The absence of observational data makes it difficult to validate or refute theories about white holes. While theoretical models provide intriguing possibilities, science relies on empirical evidence. Without direct observations, white holes remain speculative. White holes are often described in theoretical papers and models, but these remain abstract without observational support. The scientific method demands that hypotheses be tested and observed, a step that white hole theories have not yet achieved. Advances in computational simulations help scientists explore the conditions under which white holes might form. These simulations provide valuable insights but cannot replace direct observations. They highlight the need for new observational strategies and technologies. Astrophysical phenomena are typically confirmed through multiple lines of evidence. For white holes, the lack of such evidence means they are not widely accepted as real objects in the universe. This skepticism is a natural part of the scientific process. The search for white holes continues, driven by the desire to understand all possible solutions to Einstein's equations. As technology advances, the hope remains that new methods will allow us to detect or rule out the existence of white holes. Until then, they remain an open question in astrophysics. The ongoing challenge of detecting white holes underscores the importance of continued research and innovation in observational techniques. It also highlights the speculative nature of theoretical physics, where many concepts remain beyond our current capability to observe directly. Despite the lack of direct observations, some indirect evidence has been proposed to support the existence of white holes. These clues come from theoretical models and certain high-energy astrophysical phenomena that might be explained by white holes. One potential source of indirect evidence is the behavior of gamma-ray bursts. These intense bursts of gamma radiation are typically attributed to supernovae or neutron star mergers. However, some theorists suggest that they could also result from matter being expelled by a white hole. Cosmic rays are another area of interest. These high-energy particles travel through space at nearly the speed of light. While most cosmic rays are believed to originate from supernovae and other known sources, some might be the result of matter ejected from white holes. The early universe presents another potential source of indirect evidence. During the Big Bang, conditions were extreme and chaotic. Some cosmological models propose that white holes could have formed in these early moments, influencing the distribution of matter and energy we observe today. The concept of white holes is also supported by certain solutions to Einstein's field equations. These mathematical solutions predict the existence of regions in space-time where matter and energy are expelled. While these solutions are theoretical, they provide a framework for considering white holes as possible objects in the universe. Some scientists have suggested that certain anomalies in the cosmic microwave background radiation could be evidence of white holes. These anomalies might be explained by the influence of white holes in the early universe, although this idea remains speculative. The study of black holes and their evaporation through Hawking radiation has led to hypotheses about white holes. If black holes can emit radiation and lose mass over time, some theories suggest that this process could eventually lead to the formation of white holes, providing an indirect link between the two. Gravitational waves offer another potential avenue for indirect evidence. While gravitational waves from black hole mergers have been detected, waves from hypothetical white hole events could have distinctive signatures. Detecting such waves would provide strong indirect evidence for white holes. Quantum gravity theories like loop quantum gravity propose that black holes could transition into white holes through a process known as a quantum bounce. This theory suggests that what we observe as black holes today might eventually become white holes, offering a long-term perspective on their existence. Certain high-energy cosmic events, currently unexplained by conventional models, might be reinterpreted as the result of white hole activity. This reinterpretation requires more detailed study and evidence, but remains a possibility for future research. Theoretical work on the holographic principle and ADS-CFT correspondence also provides indirect support. These theories suggest that information and energy conservation laws might be upheld in ways that include the behavior of white holes, integrating them into a broader theoretical framework. Anomalies in the distribution of dark matter and dark energy might also hint at the existence of white holes. If white holes interact with these mysterious components of the universe, they could leave subtle traces that we have yet to fully understand. Some physicists propose that white holes could account for unexplained fast radio bursts, which are brief, intense flashes of radio waves. While these bursts are typically attributed to neutron stars or other dense objects, the possibility of white holes remains an intriguing alternative. Indirect evidence also comes from the study of entropy and thermodynamics. The theoretical properties of white holes challenge our understanding of these principles, suggesting that their existence could help resolve certain paradoxes in physics, such as the information paradox. Finally, advancements in simulation technology allow scientists to model the behavior of white holes under various conditions. These simulations provide a deeper understanding of how white holes might interact with their environment, offering indirect evidence through predictive modeling. Comparing the evidence for black holes with the evidence for white holes reveals stark differences. Black holes have a wealth of observational data supporting their existence. White holes, on the other hand, remain purely theoretical with no direct observations. The existence of black holes has been confirmed through various methods. The most compelling evidence comes from observing the motion of stars and gas around an invisible, massive object. These observations show stars orbiting around a point with immense gravitational pull, indicative of a black hole. Accretion disks around black holes provide another source of evidence. As matter falls into a black hole, it forms a disk and heats up, emitting X-rays. These X-ray emissions are a key indicator of black holes, observed in numerous systems across the universe. Gravitational lensing caused by black holes offers further proof. The strong gravitational field of a black hole bends the light from objects behind it, creating distinctive patterns. These patterns have been observed and match the predictions of general relativity for black holes. Gravitational waves have also confirmed the existence of black holes. Detected by observatories like LIGO, these waves are produced by the merger of black holes. The patterns of these waves provide direct evidence of black hole interactions and properties. In contrast, there is no such direct observational evidence for white holes. While theoretical models predict their existence, no white hole has been observed through stellar motions, accretion disks, gravitational lensing, or gravitational waves. The concept of Hawking radiation provides indirect evidence for black holes. This radiation is emitted due to quantum effects near the event horizon. While not yet directly observed, its theoretical predictions align well with the properties of black holes. White holes, theoretically, would emit a different kind of radiation. However, no such emissions have been detected. This lack of evidence makes it difficult to validate the existence of white holes, unlike the case with black holes. Now, black holes can be studied through their interactions with nearby objects. This includes binary systems where a black hole pulls matter from a companion star, creating observable phenomena. White holes, with their repulsive nature, would not form such systems, making them harder to detect. The evidence for black holes also includes observations of supermassive black holes at the centers of galaxies. These black holes influence the motion of stars and gas on a galactic scale, providing clear observable effects. There is no corresponding evidence for supermassive white holes. Theoretical evidence for black holes is supported by general relativity and numerous observations. White holes are also predicted by general relativity, but the lack of observational support keeps them speculative. The theoretical foundation for white holes is strong, but without observational data, they remain unconfirmed. Comparative studies of black holes and white holes highlight the differences in empirical support. Black holes have multiple lines of observational evidence, while white holes rely solely on theoretical predictions. This gap emphasizes the need for new methods to detect or refute white holes. Black hole research benefits from technological advancements in telescopes and detectors. These tools have provided increasingly detailed data, reinforcing the existence of black holes. Similar advancements are needed to explore the possibility of white holes. The scientific community widely accepts black holes due to the robust evidence. White holes, however, remain a topic of debate and exploration. The contrast in evidence underscores the different stages of understanding for these two theoretical constructs. Ultimately, the comparison between black hole and white hole evidence illustrates the importance of observational data in confirming theoretical predictions. As our observational capabilities improve, the hope is that we might one day find evidence for or against the existence of white holes. Identifying possible candidates for white hole sightings involves examining unusual cosmic phenomena. One area of interest is gamma-ray bursts. These intense, high-energy explosions could potentially be linked to white holes, although they are typically attributed to supernovae or neutron star mergers. Another candidate might be certain high-energy cosmic rays. While most cosmic rays come from known sources like supernovae, some might originate from the expulsion of matter by a white hole. This possibility remains speculative but intriguing. Fast radio bursts are another phenomenon that could hint at white holes. These brief, intense flashes of radio waves have mysterious origins. Some scientists propose that they might be connected to white holes, although this hypothesis is still under investigation. The early universe presents another opportunity for identifying white holes. Conditions just after the Big Bang were extreme, and some models suggest that white holes could have formed during this period. Evidence of these early white holes might be found in the cosmic microwave background radiation. Certain anomalies in the distribution of dark matter might also be linked to white holes. If white holes interact with dark matter, they could create detectable irregularities. Observing these irregularities could provide indirect evidence of white holes. Theoretical models predict that white holes might be highly unstable, quickly transforming into black holes or dissipating. This instability makes it difficult to observe white holes directly, but transient events in the universe might offer clues. Observations of black hole evaporation through Hawking radiation suggest another potential candidate. If black holes can emit radiation and lose mass, the final stages of this process might involve a transition to a white hole. Detecting such a transition would be groundbreaking. The behavior of certain quasars could also hint at white holes. Quasars are extremely bright and energetic, powered by supermassive black holes. If any of these objects show signs of expelling rather than consuming matter, they could be candidates for white holes. The edges of our observable universe might also hide clues. At these vast distances, the effects of white holes could be more pronounced. Advanced telescopes and observational techniques might eventually detect these distant phenomena. Simulations of cosmic phenomena can help identify potential candidates. By modeling how white holes might interact with their environment, scientists can predict observable signatures. These predictions can then guide observational efforts. Some black hole candidates might actually be white holes in disguise. If a black hole exhibits unusual behavior, such as emitting rather than accreting matter, it could be reclassified as a white hole. Careful observation and analysis are necessary to make such determinations. Gravitational wave detectors might also identify white holes. While current detections focus on black hole mergers, unique wave patterns could signal the presence of white holes. Future enhancements to these detectors could expand their capabilities. Astrophysical jets, typically associated with black holes and neutron stars, might also provide clues. If any jets are found to originate from regions expelling matter rather than accreting it, they could indicate white holes. Detailed observations are needed to confirm this. Interstellar gas clouds showing unexpected behaviors might also be linked to white holes. If a gas cloud is observed to be expelled or disrupted in a way that doesn't match known phenomena, a white hole could be responsible. Such observations would require careful verification. Finally, unusual patterns in the cosmic microwave background radiation could be revisited with white holes in mind. If existing anomalies can be better explained by the presence of white holes, this would provide compelling indirect evidence. Further analysis and improved data are essential to explore this possibility. Observing white holes presents numerous challenges due to their theoretical and elusive nature. Unlike black holes, white holes are predicted to repel matter and energy, making them fundamentally different and harder to detect. One significant challenge is their hypothetical instability. Theoretical models suggest that white holes might be highly unstable, quickly transforming into black holes or dissipating. This rapid change makes it difficult to capture direct observations. The lack of accretion disks around white holes is another obstacle. Black holes are often detected by the X-rays emitted from their accretion disks. Without such disks, white holes would not produce these observable high-energy signals. Gravitational lensing, a key method for observing black holes, may not work the same way for white holes. The repulsive nature of white holes could produce different lensing effects, making them harder to identify using this technique. Gravitational waves, which have confirmed black hole mergers, might also be challenging for white hole detection. The unique wave patterns expected from white hole interactions are not yet well understood or predicted, complicating their identification. The expulsion of matter and energy from white holes might not produce easily detectable emissions. Unlike black holes that pull in and heat matter, white holes would push matter away, potentially creating subtler signals. White holes, if they exist, might be located in regions of the universe where observational coverage is limited. Advanced and specialized telescopes may be required to detect these elusive objects, which are not yet widely available. Theoretical predictions about white hole behavior are still developing. Without clear models and expected signatures, directing observational efforts to find white holes becomes more difficult. Scientists need more refined theories to guide their searches. Many phenomena that might hint at white holes can often be explained by more conventional objects, like black holes or neutron stars. This overlap makes it challenging to distinguish potential white hole signals from other cosmic events. Technological limitations also play a role. Current instruments may not be sensitive enough to detect the subtle and unique signatures of white holes. Future advancements in observational technology are needed to overcome these limitations. The vast distances involved in cosmic observations add to the difficulty. White holes might be extremely far away, making their signals faint and challenging to separate from background noise. Improved data analysis techniques are essential. Another challenge is the transient nature of potential white hole phenomena. If white holes are short-lived, capturing their existence requires continuous and extensive monitoring, which is resource-intensive and complex. Theoretical white holes might produce unfamiliar or unexpected emissions. Without knowing exactly what to look for, astronomers face the challenge of identifying signals that do not fit established patterns of known objects. Funding and research priorities also impact the search for white holes. With many competing interests in astrophysics, securing the resources needed to pursue such speculative research can be difficult. Collaboration across various fields of physics is essential but challenging. Understanding white holes involves general relativity, quantum mechanics, and advanced computational models. Coordinating efforts among diverse scientific communities is crucial. Ultimately, the search for white holes tests the limits of our current scientific understanding and technological capabilities. Addressing these challenges requires innovative thinking, interdisciplinary collaboration, and significant advancements in both theory and observation. Hawking radiation is a theoretical prediction made by physicist Stephen Hawking in 1974. It describes how black holes can emit radiation due to quantum mechanical effects near their event horizons. This radiation causes black holes to lose mass and energy over time, potentially leading to their eventual evaporation. The concept of Hawking radiation arises from the principles of quantum mechanics and general relativity. Near the event horizon of a black hole, quantum fluctuations occur, producing pairs of particles and antiparticles. Normally, these pairs annihilate each other, but near the event horizon, one particle can fall into the black hole, while the other escapes. The particle that escapes carries away energy from the black hole, which is observed as Hawking radiation. The particle that falls into the black hole effectively reduces the black hole's mass. This process leads to the gradual evaporation of the black hole over incredibly long timescales. Hawking radiation is significant because it suggests that black holes are not completely black. Instead, they emit radiation and lose mass, challenging the idea that nothing can escape from a black hole. This insight bridges the gap between quantum mechanics and general relativity. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. Smaller black holes emit radiation at higher temperatures, while larger black holes emit cooler radiation. This relationship means that microscopic black holes, if they exist, would evaporate much more quickly than stellar mass black holes. The discovery of Hawking radiation has profound implications for the information paradox. According to quantum mechanics, information about physical states should never be lost. However, if a black hole evaporates completely, what happens to the information it contains? This paradox remains a major question in theoretical physics. Hawking's prediction also led to the concept of black hole entropy. The idea that black holes have entropy and temperature suggests they follow the laws of thermodynamics. The entropy of a black hole is proportional to the area of its event horizon, linking thermodynamics and gravitational physics. Despite its theoretical basis, Hawking radiation has not yet been observed directly. The radiation emitted by black holes is incredibly weak and difficult to detect with current technology. Observing Hawking radiation would require extremely sensitive instruments capable of measuring faint signals from distant black holes. Experiments to detect analogues of Hawking radiation in laboratory settings are ongoing. Researchers use systems that mimic the conditions near a black hole's event horizon, such as sonic black holes in fluids, to study the emission of radiation. These experiments aim to provide indirect evidence supporting Hawking's prediction. Hawking radiation has implications for the ultimate fate of black holes. Over vast timescales, black holes could lose enough mass to eventually evaporate completely. This process suggests that even the most massive black holes are not eternal, but rather have finite lifespans. The concept also influences the study of primordial black holes. These hypothetical black holes, formed in the early universe, would be small enough to evaporate through Hawking radiation within the age of the universe. Detecting their remnants could provide insights into the early universe and the nature of black holes. Hawking radiation is a key element in the study of quantum gravity. It represents a situation where both quantum mechanics and general relativity must be considered, offering a potential pathway to understanding how these two fundamental theories can be unified. Theoretical work on Hawking radiation continues to evolve. Researchers are exploring how this radiation interacts with other quantum fields and what it reveals about the structure of space-time near a black hole. These studies push the boundaries of our understanding of the universe. Stephen Hawking's work on black hole radiation has had a lasting impact on physics. It has opened new avenues of research and inspired countless studies aimed at understanding the nature of black holes and the fundamental laws of the universe. Hawking radiation remains a testament to the power of theoretical physics. Even without direct observational evidence, its implications challenge and expand our understanding of some of the most extreme and mysterious objects in the cosmos. The black hole evaporation process begins with the emission of Hawking radiation. This radiation is a result of quantum fluctuations near the event horizon of the black hole. As particle-antiparticle pairs form, one particle falls into the black hole while the other escapes. The escaping particle takes energy away from the black hole. This loss of energy translates into a decrease in the black hole's mass. Over time, this continuous process causes the black hole to lose more and more mass. As the black hole loses mass, the temperature of the emitted Hawking radiation increases. Smaller black holes emit radiation more intensely. This increased radiation accelerates the loss of mass, leading to a faster evaporation rate. The final stages of black hole evaporation are the most dramatic. When the black hole becomes extremely small, the radiation it emits is incredibly energetic. This intense emission causes the black hole to evaporate rapidly in a burst of high-energy particles. The end of the evaporation process is marked by the complete disappearance of the black hole. Theoretically, all that remains is the radiation that was emitted throughout the black hole's lifetime. The black hole itself no longer exists. One of the most profound implications of black hole evaporation is the information paradox. If a black hole evaporates completely, what happens to the information contained within it? This paradox challenges our understanding of quantum mechanics and general relativity. Some theories suggest that the information might be encoded in the Hawking radiation itself. However, how this encoding works and whether it preserves all information is still a topic of intense debate. Resolving this paradox could lead to major breakthroughs in physics. The evaporation process has implications for the fate of primordial black holes. These black holes, formed in the early universe, could have evaporated by now if they were small enough. Detecting the remnants of such evaporated black holes could provide insights into the early universe. Primordial black holes that are still evaporating today might be sources of high-energy cosmic rays. Observing these emissions could offer indirect evidence of black hole evaporation and help confirm theoretical predictions. Black hole evaporation also impacts our understanding of black hole thermodynamics. The relationship between a black hole's mass, temperature, and entropy is crucial. As black holes evaporate, their entropy decreases, raising questions about the fundamental laws of thermodynamics. Studying the evaporation process helps physicists explore the interface between quantum mechanics and general relativity. This intersection is key to developing a theory of quantum gravity, which aims to describe all fundamental forces in a unified framework. Theoretical models of black hole evaporation are continually refined. Advances in computational physics allow scientists to simulate the process in greater detail. These simulations help test the predictions of Hawking's theory and explore new aspects of black hole physics. Experimental efforts to observe analogues of Hawking radiation in the lab contribute to our understanding. Systems that mimic the conditions near a black hole's event horizon provide valuable data. These experiments offer indirect support for the theoretical predictions. The complete evaporation of a black hole would release all its energy back into the universe. This energy release could have significant astrophysical implications, influencing the surrounding space and potentially detectable by future instruments. Understanding the black hole evaporation process is crucial for comprehending the life cycle of black holes. It highlights the dynamic nature of these cosmic objects and their role in the universe, from their formation to their ultimate demise. Entropy considerations for white holes present unique challenges. In black holes, entropy is directly related to the area of the event horizon. This relationship is a cornerstone of black hole thermodynamics. For white holes, the concept of entropy is less clear. Since white holes theoretically expel matter and energy, their entropy dynamics could be fundamentally different from those of black holes. The second law of thermodynamics states that entropy in a closed system should never decrease. If white holes expel matter, one might wonder if this process could result in a decrease in entropy, which would violate this fundamental law. One possibility is that the expulsion of matter and energy from a white hole could actually increase the entropy of the surrounding universe. By spreading energy outwards, white holes might contribute to a net increase in universal entropy. Another consideration is how the entropy of a white hole compares to that of a black hole. If a black hole transitions into a white hole, as some theories suggest, the entropy must change in a way that respects the second law of thermodynamics. The idea of a quantum bounce, where a black hole turns into a white hole, involves a significant shift in entropy. Understanding this transition requires a deeper exploration of quantum gravity and how it governs these processes. Some physicists propose that the entropy of a white hole could be related to the information it expels. If white holes release information encoded in the expelled matter, this process could help reconcile the apparent decrease in entropy. Theoretical models must account for the thermodynamic properties of white holes. These models explore how the entropy of a white hole evolves over time and what factors influence it. This remains an active area of research in theoretical physics. Loop quantum gravity offers one framework for considering the entropy of white holes. This theory suggests that the granular structure of spacetime could affect how entropy is calculated and conserved during the formation of a white hole. The holographic principle, which posits that all the information in a volume of space can be described by a theory on the boundary of that space, might also apply to white holes. This principle could provide insights into how entropy is managed in these exotic objects. Entropy considerations for white holes might also involve exotic states of matter and energy. The extreme conditions near a white hole's event horizon could produce unique thermodynamic effects not seen elsewhere in the universe. Understanding the entropy of white holes could shed light on the broader principles of thermodynamics in extreme environments. This knowledge would be valuable for studying other high-energy astrophysical phenomena. The entropy of white holes might also have implications for cosmology. If white holes played a role in the early universe, their entropy dynamics could influence the evolution and structure of the cosmos. Researchers continue to explore the theoretical underpinnings of white hole entropy. Advances in mathematical modeling and quantum theory are crucial for developing a coherent understanding of these processes. Entropy considerations for white holes highlight the complexity and interconnectedness of fundamental physics. As our understanding evolves, it will reveal deeper insights into the nature of the universe and the laws that govern it. The thermodynamic implications of white holes present a fascinating challenge to our understanding of the universe. In black holes, the laws of thermodynamics are well studied, with entropy being a key factor. For white holes, these principles might behave differently. One major implication is how the second law of thermodynamics applies. This law states that the total entropy of a closed system cannot decrease. If white holes expel matter and energy, we must understand how this affects the overall entropy of the universe. The expulsion process could theoretically increase the entropy of the surrounding space. As white holes push out matter, they could distribute energy more widely, contributing to the overall increase in entropy, thus aligning with the second law. Considering the temperature of white holes, it's unclear how it would be defined. For black holes, temperature is inversely proportional to their mass. White holes might have a different temperature profile, impacting how they interact thermodynamically with their environment. The idea of negative entropy or negentropy has been suggested in some models. If white holes reduce entropy locally while increasing it globally, this would present a new aspect of thermodynamics that we need to explore further. Thermodynamics also involves the concept of energy conservation. In white holes, understanding how energy is expelled and conserved presents unique challenges. The repulsion of matter must comply with the conservation laws, adding complexity to the thermodynamic analysis. The relationship between entropy and the event horizon in white holes is another area of interest. For black holes, entropy is proportional to the area of the event horizon. It remains to be seen if a similar relationship exists for white holes and how it would be quantified. The potential transition from black holes to white holes, as suggested by some quantum gravity theories, brings about significant thermodynamic considerations. Such a transition would need to account for changes in entropy and energy states in a coherent manner. Thermodynamic equilibrium is another principle to consider. In most systems, equilibrium is reached when entropy is maximized. White holes, constantly expelling matter, might never reach equilibrium, challenging our current understanding of thermodynamic processes. White holes could also impact the thermodynamic properties of the universe on a large scale. If they were prevalent in the early universe, their thermodynamic interactions might have influenced cosmic evolution and the current state of matter and energy distribution. The study of white holes could lead to new insights into the nature of entropy and energy in extreme conditions. These insights might not only apply to astrophysics, but could also influence other fields such as quantum mechanics and cosmology. Examining the thermodynamics of white holes might also provide clues about the unification of general relativity and quantum mechanics. Understanding how these laws operate at the event horizons of white holes could bridge gaps between these two fundamental theories. Theoretical models continue to evolve, providing new ways to explore the thermodynamic implications of white holes. These models use advanced mathematics and simulations to predict how white holes might behave under different conditions. Experimental analogues, such as sonic black holes, could offer indirect insights. By studying these systems in the lab, scientists might infer some thermodynamic properties of white holes, furthering our understanding of these exotic objects. Ultimately, the thermodynamic implications of white holes challenge us to rethink and expand our understanding of fundamental physics. As research progresses, it will uncover new layers of complexity and interconnection within the universe. The second law of thermodynamics is a fundamental principle stating that the total entropy of an isolated system can never decrease over time. This law is crucial in understanding the behavior of physical systems, including hypothetical white holes. White holes, by definition, expel matter and energy. If this expulsion leads to a decrease in the system's entropy, it would seem to contradict the second law. However, The overall impact on the universe's entropy must be considered to see if it aligns with thermodynamic principles. When white holes eject matter and energy, they could increase the entropy of the surrounding space. This dispersal of energy could contribute to a net increase in the universe's entropy, thus maintaining compliance with the second law. The idea of white holes challenges traditional thermodynamic views. While black holes increase entropy by absorbing matter, white holes might do so by spreading it out. This process could offer a novel way of thinking about entropy dynamics in the cosmos. To reconcile white holes with the second law, we must consider their interactions with the environment. The expelled matter would mix with the surrounding space, leading to increased disorder or entropy, consistent with thermodynamic expectations. The second law also implies that energy transformations are irreversible. For white holes, the process of expelling matter must be irreversible, ensuring that the entropy of the entire system increases over time, even if locally it might seem to decrease. The concept of white holes and the second law brings attention to the nature of time's arrow. If white holes are time-reversed black holes, their behavior might provide insights into the directionality of time and how entropy governs this flow. Entropy in white holes could be tied to information. The information paradox concerning black holes suggests that information cannot be lost. If white holes release this information, they could uphold the second law by ensuring no decrease in total entropy. Thermodynamic equilibrium is another aspect to consider. White holes constantly expelling energy may never reach equilibrium. This persistent outflow aligns with the second law by continually increasing the entropy of their surroundings. The theoretical transition from black holes to white holes involves significant entropy changes. For this transition to respect the second law, the total entropy before and after must reflect an increase, suggesting complex thermodynamic processes at play. In cosmological terms, if white holes existed in the early universe, their contribution to entropy could have been substantial. This early increase in entropy might have influenced the universe's evolution, consistent with the second law. The study of white holes and the second law can also impact our understanding of thermodynamic limits. Exploring how these objects comply with or challenge these limits can reveal deeper principles governing energy and entropy in extreme environments. Quantum mechanics may offer additional insights. Quantum processes near a white hole's event horizon could affect how entropy is generated and maintained, providing a more nuanced understanding of how white holes fit within thermodynamic laws. Ultimately, white holes must adhere to the second law of thermodynamics. Their role in increasing the universe's total entropy, despite their unique properties, underscores the universality of thermodynamic principles. Continued research into the connection between white holes and the second law will deepen our understanding of these hypothetical objects and their place in the universe. This research could lead to significant advances in both theoretical and applied physics. The concept of wormholes in physics is a fascinating topic that bridges the realms of theoretical and speculative science. Wormholes are hypothetical tunnels connecting two separate points in space-time, potentially allowing for faster-than-light travel between them. Albert Einstein and Nathan Rosen first introduced the idea of wormholes in 1935, through what is known as the Einstein-Rosen bridge. This solution to Einstein's field equations describes a bridge between two black holes or a black hole and a white hole. Wormholes are often depicted as shortcuts through space-time. If they exist, they could connect distant regions of the universe, making travel across vast cosmic distances theoretically possible in a shorter time than it would take to travel through normal space. The concept of traversable wormholes was further developed by physicist Kip Thorne and his colleagues in the late 20th century. They explored the conditions under which a wormhole could remain open and stable, allowing matter to pass through it without collapsing. A key challenge with wormholes is their stability. For a wormhole to remain open, it would require a form of negative energy or exotic matter to counteract the gravitational forces that would otherwise cause it to collapse. This exotic matter has not been observed and remains purely theoretical. If stable wormholes exist, they could have profound implications for our understanding of causality and time travel. The ability to connect different points in space-time could potentially allow for travel into the past or future, raising complex questions about the nature of time and causality. In theoretical models, a wormhole's two ends could be located anywhere in space-time, such as different galaxies, different points in time, or even different universes. This versatility makes wormholes an intriguing subject for both scientific and science fiction narratives. The mathematics of wormholes involves solving the Einstein field equations under specific conditions. These solutions, while possible on paper, face significant challenges when it comes to physical realization and stability in our universe. Theoretical physicist John Archibald Wheeler coined the term wormhole and contributed significantly to the study of these structures. His work helped popularize the concept and inspired further research into their properties and potential applications. Experimental evidence for wormholes is currently non-existent. While they are a popular topic in theoretical physics and cosmology, no direct or indirect observations have confirmed their existence. This lack of evidence keeps wormholes firmly in the realm of theoretical speculation. Quantum mechanics and wormholes intersect in fascinating ways. Some theories suggest that tiny quantum-scale wormholes might exist, connecting different regions of space on a microscopic level. These quantum wormholes could potentially have implications for the fundamental structure of spacetime. The idea of using wormholes for interstellar travel has captivated imaginations for decades. If we could harness or create stable wormholes, it might open up the possibility of exploring distant star systems and even other galaxies, revolutionizing space travel. Stephen Hawking and other physicists have debated the feasibility of wormholes and their implications for information transfer and the laws of physics. These discussions continue to drive research and inspire new theories in the field of gravitational physics. Wormholes also play a role in discussions about the unification of general relativity and quantum mechanics. Understanding how wormholes might function at both macroscopic and quantum scales could provide insights into a theory of quantum gravity. As a concept, wormholes challenge our understanding of the universe and push the boundaries of what is scientifically conceivable. They remain an exciting and speculative topic, inspiring both scientific inquiry and imaginative exploration of what might be possible in the cosmos. White holes as potential wormhole exits present a fascinating theoretical scenario. If wormholes connect different points in spacetime, one end could be a black hole while the other could be a white hole. This arrangement would create a bridge between regions or even different universes. In this model, the black hole end of the wormhole would pull matter in. Anything that crosses the event horizon would travel through the wormhole. Instead of being crushed at a singularity, it could emerge from the white hole on the other side. The white hole, as the exit point, would expel the matter and energy that entered the black hole. This process would effectively make the wormhole a tunnel through spacetime. The repulsive nature of white holes fits this role, ejecting matter rather than consuming it. This concept raises interesting possibilities for space travel. If stable wormholes exist with white holes as exits, they could allow rapid travel across vast distances. The time to traverse the wormhole could be significantly less than traveling through normal space. One challenge is the stability of such wormholes. Maintaining a stable connection requires exotic matter or negative energy. Without this, the wormhole could collapse, making safe passage impossible. Theoretical models continue to explore how such stability could be achieved. If white holes serve as wormhole exits, they could help explain the conservation of information. Information and matter entering a black hole would not be lost but rather expelled by the white hole. This idea aligns with some solutions to the information paradox. However, this scenario is purely theoretical. No observational evidence currently supports the existence of white holes or wormholes. These ideas remain speculative, but provide intriguing possibilities for future research and exploration. The interaction between the black hole and white hole ends of a wormhole would need to be precisely balanced. Any disturbance could disrupt the connection, causing the wormhole to collapse. This delicate balance presents a significant challenge to the stability of such structures. Theoretical physicists continue to develop models that could support the existence of wormholes with white hole exits. These models often rely on advanced mathematics and quantum theories. They aim to find conditions under which these exotic structures could exist. If wormholes with white hole exits exist, they might leave detectable signatures. These could include unique gravitational wave patterns or unusual radiation emissions. Observational efforts might eventually find indirect evidence supporting these theories. The possibility of time travel also arises with wormholes. Traveling through a wormhole with a white hole exit could mean moving not only across space, but also time. This raises complex questions about causality and the nature of time itself. The connection between black holes and white holes through wormholes challenges our understanding of space-time. It suggests a universe more interconnected and dynamic than previously thought. This interconnectedness could have profound implications for cosmology and physics. Some scientists speculate that white holes as wormhole exits could help resolve certain cosmological puzzles. They might offer explanations for high-energy phenomena that are currently not well understood. This potential adds to the allure of studying these theoretical structures. The idea of white holes as wormhole exits also captivates the public imagination. It features prominently in science fiction, inspiring stories about interstellar travel and the exploration of distant worlds. This cultural impact highlights the power of theoretical physics to spark imagination. Research into white holes and wormholes continues to push the boundaries of our understanding. While these concepts remain speculative, they drive innovation in theoretical physics. They challenge us to think beyond our current knowledge and explore the possibilities that lie at the frontier of science. Theoretical time travel implications of white holes and wormholes are profound and fascinating. If white holes serve as exits for wormholes, they could allow for travel not only through space, but also through time. This dual nature challenges our understanding of causality and the nature of the universe. Wormholes, in theory, could connect different points in time as well as space. Entering a black hole and exiting through a white hole might place the traveler at a different time, either in the past or future. This raises complex questions about the nature of time and temporal relationships. One implication of time travel through wormholes is the potential for causal paradoxes. If a traveler could move back in time, they might alter events in ways that could create contradictions, such as the famous grandfather paradox. This paradox questions what happens if a traveler prevents their own existence by altering the past. Theoretical models often address these paradoxes by proposing self-consistent histories. In these models, any actions taken by a time traveler are already part of history, ensuring that paradoxes cannot occur. This concept maintains consistency, but challenges our intuitive understanding of free will and determinism. Quantum mechanics might offer solutions to these paradoxes through the many worlds interpretation. According to this interpretation, traveling back in time could create a new, branching timeline, avoiding paradoxes by placing the traveler in a different universe where their actions do not affect the original timeline. Another intriguing implication is the potential for closed time-like curves. These curves are paths in space-time that loop back on themselves, allowing for the possibility of returning to an earlier point in time. Wormholes with white hole exits might create such curves, enabling time travel loops. The energy requirements for maintaining a stable wormhole capable of time travel are immense. Exotic matter or negative energy would be necessary to keep the wormhole open. Currently, such materials are purely theoretical and have not been observed. Theoretical time travel also raises questions about information preservation. If information can travel back in time, it must be accounted for in a way that does not violate the laws of physics. This ties into the information paradox associated with black holes and white holes. Relativity theory suggests that moving through a wormhole could involve extreme time dilation. Time for the traveler might pass differently than for an outside observer, potentially allowing the traveler to reach distant futures without aging significantly themselves. The potential for time travel through white holes and wormholes opens up speculative possibilities for communication across time. Sending messages to the past or future could revolutionize our understanding of history and future planning, though it remains firmly in the realm of speculation. Another consideration is the impact on entropy and the second law of thermodynamics. Time travel could theoretically affect the direction of entropy, leading to scenarios where entropy decreases locally while increasing globally, maintaining overall thermodynamic consistency. Theoretical physicists continue to explore these implications using advanced mathematical models and simulations. These studies aim to understand the conditions under which time travel might be possible and the physical laws that would govern it. Practical time travel remains far beyond our current technological capabilities. Even if wormholes and white holes exist, creating or stabilizing them for time travel poses enormous challenges that might never be overcome. Time travel theories often intersect with philosophical questions about the nature of reality and human experience. They force us to consider the implications of altering the past or foreseeing the future, raising ethical and existential questions. Ultimately, the theoretical time travel implications of white holes and wormholes push the boundaries of our imagination and scientific understanding. They encourage us to explore the limits of physics and consider the profound mysteries that still await discovery in the universe. Stability issues of wormholes are a major concern in theoretical physics. For a wormhole to be traversable, it must remain open long enough for matter to pass through. This requires conditions that are not easily met in our current understanding of physics. One key issue is the need for exotic matter. To counteract the immense gravitational forces that would otherwise collapse the wormhole, negative energy or exotic matter with negative mass is required. This type of matter has not been observed and remains a theoretical construct. Theoretical models often assume the presence of exotic matter to keep a wormhole stable. However, producing or even detecting such matter is beyond our current technological capabilities. This limitation makes practical wormhole travel highly speculative. Even if exotic matter exists, the quantities required to stabilize a wormhole might be enormous. The energy needed could be equivalent to that of entire stars, making the engineering challenges daunting. This presents a significant barrier to creating stable wormholes. Another stability issue is the potential for quantum fluctuations. At the quantum level, space-time is not perfectly smooth, but instead exhibits constant fluctuations. These fluctuations could destabilize a wormhole, causing it to collapse before anything can traverse it. The interaction between a wormhole and surrounding matter is also problematic. Matter passing through or near the wormhole could alter its structure, leading to instability. This sensitivity to external influences makes maintaining a stable wormhole challenging. Relativity suggests that any mass entering a wormhole would increase its gravitational pull, potentially causing it to collapse. Balancing this increase with the repulsive effect of exotic matter requires precise conditions that are difficult to achieve. There is also the issue of tidal forces within the wormhole. As matter travels through, the gravitational forces could stretch and compress it to extreme degrees. These tidal forces could not only harm travelers, but also affect the stability of the wormhole itself. Wormholes might also suffer from what is known as the chronology protection conjecture. Proposed by Stephen Hawking, this conjecture suggests that the laws of physics might prevent time travel to avoid paradoxes. If true, this would inherently destabilize wormholes that allow for time travel. Maintaining a wormhole open for long periods poses another challenge. Even if a wormhole could be created and stabilized momentarily, keeping it open indefinitely requires continuous input of exotic matter and energy, posing significant practical difficulties. Cosmic radiation and other high-energy particles could interact with the wormhole, potentially leading to instabilities. These interactions would need to be carefully managed to maintain the wormhole's stability over time. The theoretical models of wormholes often rely on simplifying assumptions that might not hold in the real universe. For example, assuming perfect symmetry or ignoring certain physical effects could lead to overestimating the stability of wormholes. Advanced mathematical models and simulations are used to study wormhole stability. These models help identify the precise conditions needed for stability, but also highlight the complexities and challenges involved. Even small perturbations could cause a wormhole to collapse. This sensitivity to initial conditions means that any practical attempt to create a wormhole would need to control numerous variables with extreme precision. Ultimately, the stability issues of wormholes underscore the speculative nature of these constructs. While they provide exciting possibilities in theoretical physics, the practical challenges are immense. Continued research is needed to explore whether stable wormholes could ever exist in our universe. Popular science fiction representations of wormholes often depict them as portals for instant travel across vast distances. In these stories, wormholes are stable, easily navigable, and conveniently located, making them a staple of interstellar travel. One of the most famous depictions is in the television series Stargate. The Stargate is a device that creates a stable wormhole, allowing characters to travel instantaneously to different planets. This concept makes wormholes accessible and central to the storyline. In Interstellar, the film directed by Christopher Nolan, wormholes play a crucial role in the plot. The characters travel through a wormhole near Saturn to reach a distant galaxy, exploring the potential of wormholes for intergalactic travel. The Star Trek franchise frequently uses wormholes as plot devices. In Star Trek Deep Space Nine, a stable wormhole connects the Alpha Quadrant to the distant Gamma Quadrant, facilitating encounters with new civilizations and driving the series' narrative. In the Marvel Cinematic Universe, wormholes are often depicted as portals used by characters to move quickly across space. The Bifrost in the Thor movies and the portals in Doctor Strange showcase wormholes as magical or advanced technological constructs. Contact, based on Carl Sagan's novel, presents a scientifically plausible depiction of wormholes. The protagonist travels through a wormhole created by an advanced alien civilization, exploring themes of communication and discovery. In Farscape, wormholes are a central plot element, with the main character using them to travel to a distant part of the universe. The show explores the unpredictability and danger of navigating wormholes, adding a layer of suspense. The Expanse series features ring gates, which function similarly to wormholes, allowing ships to travel instantly between different star systems. This technology dramatically alters the geopolitical landscape of the series. In the video game Mass Effect, the mass relays act as gateways for faster-than-light travel, akin to wormholes. These structures are central to the game's plot, facilitating exploration and conflict across the galaxy. Sliders is a television show where characters travel through wormholes to parallel universes. Each episode explores different alternate realities, showcasing the versatility of wormholes in science fiction storytelling. The Stargate movie and subsequent TV series have popularized the concept of a network of wormholes. This network allows for exploration and adventure across different worlds, emphasizing the strategic importance of controlling wormhole technology. In Doctor Who, the TARDIS travels through the time vortex, which functions similarly to a wormhole. This allows the Doctor to journey through time and space, encountering various historical and futuristic scenarios. The film Event Horizon presents a darker take on wormholes. A spaceship designed to create a wormhole for faster-than-light travel ends up in a hellish alternate dimension, highlighting the potential dangers of such technology. In Babylon 5, jump gates create stable wormholes that allow ships to travel through hyperspace. This system forms the backbone of interstellar travel and commerce within the show's universe. Science fiction often uses wormholes to explore themes of exploration, connection, and the unknown. These representations, while imaginative, inspire real scientific inquiry into the possibilities of wormholes and their role in our understanding of the universe. The intersection of quantum mechanics and general relativity represents one of the greatest challenges in modern physics. These two foundational theories describe different aspects of the universe. Quantum mechanics governs the small scale, while general relativity governs the large scale. Quantum mechanics deals with the behavior of particles at the atomic and subatomic levels. It is characterized by principles like wave-particle duality, superposition, and entanglement. These principles describe how particles interact and exist in multiple states simultaneously. General relativity, on the other hand, describes the gravitational force as the curvature of space-time caused by mass and energy. This theory has been incredibly successful in explaining phenomena such as the bending of light around massive objects and the expansion of the universe. Combining these two theories into a single framework has proven difficult. The main issue is that the mathematical formulations of quantum mechanics and general relativity are fundamentally different. Quantum mechanics relies on probabilities and uncertainties, while general relativity uses deterministic equations. One of the key problems in merging these theories is dealing with singularities. In general relativity, singularities are points where the curvature of space-time becomes infinite, such as at the center of black holes. Quantum mechanics struggles to describe these extreme conditions. String theory is one approach to unifying quantum mechanics and general relativity. It proposes that fundamental particles are not point-like but rather one-dimensional strings that vibrate at different frequencies. This theory aims to reconcile the two by providing a framework that incorporates both quantum mechanics and gravity. Loop quantum gravity is another approach. It attempts to quantize space-time itself. suggesting that spacetime has a discrete structure at the smallest scales. This theory seeks to remove the singularities predicted by general relativity, offering a new way to understand black holes and the Big Bang. The holographic principle is a concept that also bridges these theories. It suggests that all the information contained within a volume of space can be described by a theory on the boundary of that space. This principle has implications for understanding black holes and the nature of spacetime. The study of black holes is a key area where quantum mechanics and general relativity intersect. Hawking radiation, for instance, is a quantum mechanical effect that occurs near a black hole's event horizon, leading to the gradual evaporation of the black hole. This phenomenon combines elements of both theories. Experiments in particle physics, such as those conducted at the Large Hadron Collider, provide insights into the fundamental forces of nature. These experiments probe the conditions that might reveal new physics, potentially offering clues about how to unify quantum mechanics and general relativity. Quantum field theory in curved spacetime is a framework that applies quantum mechanics in the context of general relativity. This theory studies how quantum fields behave in a curved spacetime background, contributing to our understanding of phenomena like Hawking radiation. The search for a theory of quantum gravity continues to be a central focus of theoretical physics. Researchers are exploring various models and hypotheses, hoping to find a consistent and testable theory that integrates the principles of both quantum mechanics and general relativity. The intersection of these theories also has implications for our understanding of the early universe. The conditions just after the Big Bang involve extremely high energies and densities, where both quantum effects and gravitational effects are significant. Quantum cosmology is an emerging field that applies quantum principles to the entire universe. It aims to understand the origin and evolution of the universe by integrating quantum mechanics with general relativity, offering potential explanations for cosmic phenomena. The effort to reconcile quantum mechanics and general relativity pushes the boundaries of our knowledge. It challenges us to develop new theories and technologies, driving scientific progress and deepening our understanding of the fundamental nature of reality. Quantum tunneling is a phenomenon where particles pass through a barrier that they classically shouldn't be able to cross. This effect arises from the wave-like nature of particles in quantum mechanics. In classical physics, a particle with insufficient energy to overcome a barrier would be reflected back. However, in quantum mechanics, particles have a probability of tunneling through the barrier, even if they don't have enough energy. One of the most well-known applications of quantum tunneling is in nuclear fusion. In the core of stars, hydrogen nuclei fuse to form helium, a process that involves tunneling through the Coulomb barrier created by their positive charges repelling each other. Quantum tunneling is also essential in the operation of modern electronic devices. Tunneling diodes and transistors, which are foundational components of semiconductors, rely on this effect to function, enabling the development of computers and other electronic devices. In biological systems, quantum tunneling plays a role in processes like photosynthesis. Electrons tunnel between molecules in reaction centers, allowing energy transfer with high efficiency, which is crucial for the conversion of sunlight into chemical energy. The Scanning Tunneling Microscope, STM, is a powerful tool that uses quantum tunneling to image surfaces at the atomic level. By scanning a sharp tip close to a surface, electrons tunnel between the tip and the surface, allowing the STM to create detailed images of atomic structures. Quantum tunneling also has implications for our understanding of radioactive decay. Certain types of decay, such as alpha decay, involve particles tunneling out of the nucleus, leading to the emission of radiation. The phenomenon is crucial in understanding the early universe. Quantum tunneling could have played a role in processes like cosmic inflation, where the universe underwent rapid expansion due to the tunneling of fields through potential barriers. In the context of black holes, quantum tunneling is related to Hawking radiation. Particles can tunnel out of the event horizon, leading to the gradual evaporation of the black hole over time, a process that combines quantum mechanics with general relativity. Quantum tunneling challenges our classical intuitions about energy and barriers. It highlights the probabilistic nature of quantum mechanics, where particles have a non-zero chance of being found in classically forbidden regions. The probability of tunneling decreases exponentially with the thickness and height of the barrier. However, even thick barriers can be tunneled through if particles have sufficient wave-like properties. showcasing the strange and counterintuitive nature of quantum mechanics. Researchers are exploring the potential of quantum tunneling in developing new technologies, such as quantum computers. Quantum bits or qubits can leverage tunneling to perform computations that are infeasible for classical computers, potentially revolutionizing the field of computation. Quantum tunneling also has philosophical implications, challenging our understanding of determinism and causality. The fact that particles can probabilistically pass through barriers raises questions about the nature of reality and the limits of human knowledge. Experimental verification of quantum tunneling continues to advance, with increasingly precise measurements confirming its predictions. These experiments not only validate quantum mechanics, but also open new avenues for scientific exploration and technological innovation. Ultimately, quantum tunneling is a fundamental aspect of the quantum world. It underscores the differences between classical and quantum physics, and continues to inspire curiosity and discovery in both theoretical and applied science. Quantum fluctuations are temporary changes in energy that occur spontaneously in a vacuum. They arise due to the Heisenberg uncertainty principle, which states that it is impossible to know both the position and momentum of a particle precisely at the same time. These fluctuations mean that particles and antiparticles can briefly appear and disappear, even in empty space. This phenomenon challenges the classical idea of a vacuum as completely empty and devoid of activity. Quantum fluctuations play a crucial role in the early universe. During the period of cosmic inflation, tiny fluctuations were stretched to macroscopic scales, seeding the formation of galaxies and large-scale structures in the universe. In the context of black holes, quantum fluctuations near the event horizon can lead to the creation of particle-antiparticle pairs. One particle may fall into the black hole while the other escapes, contributing to Hawking radiation. These fluctuations also have implications for the stability of the vacuum itself. The concept of vacuum energy, arising from quantum fluctuations, is associated with dark energy, which is thought to drive the accelerated expansion of the universe. Quantum fluctuations are fundamental to the concept of virtual particles. These particles exist briefly and cannot be directly observed, but their effects can be detected, influencing interactions between real particles. In particle physics, quantum fluctuations are essential for understanding forces and interactions. They contribute to the forces mediated by gauge bosons, such as the electromagnetic and weak forces, by allowing particles to exchange virtual particles. The Casimir effect is a direct manifestation of quantum fluctuations. It occurs when two uncharged metallic plates are placed close together in a vacuum, resulting in an attractive force due to the restriction of fluctuating electromagnetic fields between the plates. Quantum fluctuations also play a role in the phenomenon of quantum tunneling. They allow particles to temporarily acquire the energy needed to pass through potential barriers, leading to effects like alpha decay in radioactive materials. In the realm of quantum field theory, fluctuations in the fields represent the zero-point energy of the vacuum. This energy is present even at absolute zero temperature and has measurable effects on physical systems. These fluctuations are also thought to be responsible for the creation of black holes and white holes in some theoretical models. The dynamic nature of spacetime at the quantum level can lead to the formation of these exotic objects. In cosmology, quantum fluctuations are considered in models of the multiverse. Fluctuations in different regions of spacetime could lead to the creation of separate, causally disconnected universes with varying physical properties. Understanding quantum fluctuations is crucial for developing a theory of quantum gravity. Since these fluctuations affect spacetime on the smallest scales, they must be incorporated into any comprehensive theory that unifies quantum mechanics and general relativity. In technology, harnessing quantum fluctuations could lead to advancements in quantum computing and communication. The unpredictable nature of these fluctuations can be used to generate true random numbers, which are essential for secure cryptographic systems. Ultimately, quantum fluctuations underscore the inherent uncertainty and dynamism of the quantum world. They challenge classical notions of stability and emptiness, revealing a universe teeming with activity at the smallest scales. Potential quantum signatures of white holes are an intriguing area of research. Detecting these signatures could provide indirect evidence for the existence of white holes. One possible signature is the unique radiation emitted by a white hole, different from the Hawking radiation of black holes. This radiation might exhibit distinct energy spectra. Unlike the thermal spectrum of black hole radiation, white hole emissions could have non-thermal characteristics, helping to differentiate between the two. Quantum fluctuations near a white hole's event horizon could also produce observable effects. These fluctuations might create particles in a manner similar to Hawking radiation, but the pattern and intensity could differ. The behavior of entangled particles near a white hole could offer another signature. Entanglement properties might change as particles interact with the extreme gravitational field, leading to measurable deviations from expected quantum correlations. Gravitational waves could also provide clues. While black hole mergers produce specific gravitational wave patterns, white hole interactions might generate waves with unique signatures, distinguishable by their frequency and amplitude. Quantum tunneling effects might be observable around white holes. If particles tunnel out of a white hole, the resulting emissions could have distinctive quantum mechanical properties, setting them apart from other astrophysical phenomena. Theoretical models predict that white holes might influence the surrounding vacuum energy. Changes in vacuum energy density near a white hole could affect local quantum fields, potentially producing detectable anomalies in space. White holes might also interact differently with dark matter and dark energy. These interactions could leave quantum signatures in the distribution and behavior of these mysterious components of the universe, observable through precise measurements. Quantum simulations could help identify potential signatures. By modeling white holes and their interactions with quantum fields, researchers can predict specific observable effects, guiding future observational efforts. The information paradox related to white holes might also produce quantum signatures. If information escapes from a white hole, the manner of its release could reveal unique quantum characteristics, such as specific patterns of particle emissions. Quantum decoherence around white holes could provide additional clues. The extreme conditions might cause quantum systems to lose coherence in distinctive ways, potentially measurable with advanced quantum sensors. Non-classical light, such as squeezed light, might be emitted by white holes. This type of light has reduced quantum noise in certain properties, offering another potential signature distinguishable from classical astrophysical sources. Interactions between white holes and cosmic microwave background radiation could leave imprints. These interactions might alter the radiation's properties, creating detectable anomalies in its uniformity and spectrum. Advanced detectors like those used in quantum optics and high-energy physics could be crucial in identifying these signatures. Their sensitivity to subtle quantum effects makes them ideal for searching for white hole evidence. Overall, potential quantum signatures of white holes challenge our understanding and push the boundaries of current technology. Detecting these signatures could not only confirm the existence of white holes, but also enhance our knowledge of quantum mechanics and general relativity. Quantum gravity theories aim to unify general relativity and quantum mechanics. These two pillars of modern physics describe the large-scale structure of the universe and the behavior of particles at the smallest scales, respectively. However, they are currently incompatible. One prominent approach to quantum gravity is string theory. It posits that the fundamental constituents of the universe are not point particles, but one-dimensional strings. These strings vibrate at different frequencies, giving rise to various particles and forces. String theory also predicts the existence of extra dimensions beyond the familiar 3 dimensions of space and 1 of time. These additional dimensions are compactified or curled up at scales that are currently inaccessible to experiments. Loop quantum gravity is another leading approach. This theory suggests that space-time itself has a discrete structure composed of tiny loops. These loops are on the scale of the Planck length, the smallest measurable length. Loop quantum gravity avoids the singularities predicted by general relativity, such as those at the centers of black holes. Instead, it proposes that space-time can be quantized, removing the infinities that arise in classical theories. The holographic principle is a concept that has emerged from the study of black holes and string theory. It suggests that all the information contained within a volume of space can be described by a theory on the boundary of that space, much like a hologram. One manifestation of the holographic principle is the ADAS-CFT correspondence, proposed by Juan Maldacena. This correspondence relates a gravitational theory in anti-de Sitter space to a conformal field theory on its boundary, providing a framework for understanding quantum gravity. Spin foam models are another approach within loop quantum gravity. These models represent the evolution of spin networks over time, describing how the quantum geometry of space-time changes. Spin foams provide a way to visualize the dynamics of quantum gravity. Causal dynamical triangulations is a method that constructs space-time from simple building blocks called simplices. This approach uses a path integral formulation, summing over all possible configurations of these building blocks to describe quantum space-time. Asymptotic safety is a hypothesis suggesting that gravity becomes well-behaved at high energies due to the presence of a non-trivial fixed point in the renormalization group flow. This fixed point ensures that the theory remains finite and predictive. Group field theory generalizes loop quantum gravity and spin foam models. It treats space-time as an emergent phenomenon arising from the interactions of fundamental entities described by a group field. This approach aims to unify different quantum gravity models. Twistor theory, developed by Roger Penrose, provides a geometric framework for understanding space-time and quantum fields. It represents space-time events as points in a complex mathematical space called Twistor space, offering a new perspective on quantum gravity. Non-commutative geometry extends the concepts of quantum mechanics to space-time itself. In this approach, the coordinates of space-time do not commute, leading to a modified description of geometry at the quantum level. The quest for a theory of quantum gravity also involves understanding black hole entropy and the information paradox. These problems highlight the need for a consistent framework that incorporates both gravitational and quantum principles. Ultimately, quantum gravity theories seek to reveal the fundamental nature of space-time and unify all known forces. This pursuit challenges our understanding and pushes the boundaries of theoretical physics, promising profound insights into the workings of the universe. In this video, we delve deep into the fascinating concept of white holes, exploring their theoretical underpinnings and the challenges associated with their study. We began by explaining what white holes are, emphasizing their role as the theoretical opposites of black holes, expelling matter instead of absorbing it. This led us to discuss their potential formation processes and the fundamental differences between white holes and black holes. We examined the mathematical models and theories predicting white holes, shedding light on the perspectives of leading theoretical physicists. We also explored the hypothesized quantum signatures and the significant challenges in observing these elusive objects. The discussion highlighted the major counterarguments and skepticism within the scientific community, emphasizing the current lack of empirical evidence. We covered the latest theoretical advancements and cutting-edge simulations that are driving the field forward. These include the integration of white holes into quantum gravity theories, the development of high-resolution simulations, and experimental analogues that help us understand their potential properties and behaviors. The potential connections between white holes and phenomena such as dark matter, dark energy, and the Big Bang theory were also explored. These connections could revolutionize our understanding of the universe's evolution, offering new insights into cosmic inflation, the early universe, and the interplay between dark matter and dark energy. We discussed the profound impact that the discovery and study of white holes could have on our understanding of the universe. This includes potential paradigm shifts in cosmology, the integration of white holes into existing models, and the inspiration for new theoretical and experimental approaches. In addressing ongoing and future research directions, we highlighted the importance of interdisciplinary collaboration and the development of new technologies to detect potential white hole signatures. These efforts are crucial for advancing our knowledge and potentially uncovering new aspects of the universe. Now, if you enjoyed this deep dive into the world of white holes, please like and subscribe to our channel. Don't forget to check out our other videos covering a wide range of fascinating topics in astrophysics and beyond. Your support helps us continue to bring you exciting and informative content. Thank you for watching and stay curious.